Hi, I am Aditya. I am the CEO of Automatski. Automatski makes the most powerful quantum simulators, annealers, and computers in the world. Today, I am going to demonstrate the modified HHL algorithm to you, and I will keep it extremely short. I assume you already know the theory and applications, and I also assume that Automatski has given you the context of this video. So, you will understand what I am going to show you. If you received this video by mistake and don't know what this is all about, just ignore it. I'm here to tell you what we have achieved and not how we have achieved it. All our millennium breakthroughs are completely our own inventions without any collaboration or help from absolutely anyone else. The implementation details of all our inventions will remain a secret for the next 1,000 years. If that doesn't work for you, you should stop watching this video right now. Now, HHL is a quantum algorithm used to solve a linear system of equations. The main limitation of the HHL algorithm is that the solution to the linear system is obtained as a quantum state, not as the values of the variables or the values of the results. It is obtained as a quantum state. Thus, we cannot determine the full vector x, which is the classical solution, cannot be determined directly without running the algorithm an exponential number of times. Nobody talks about this. And the matrix A has to be S sparse or K sparse or whatever. This means that A must have at most S non-zero entries per row or column. This is a condition for the HHL algorithm. Also, the ratio of the maximum and minimum eigenvalues is called the condition number. If the condition number is larger, the system is harder to solve, and if it is smaller, the system is easier to solve on a quantum computer. Lastly, it has been shown that everything said and done, the apparent advantage of HHL algorithm can be efficiently replicated using classical algorithms with suitable data access, a process known as dequantization. So when people talk about quantum machine learning having exponential advantage over classical systems or HHL algorithm having exponential advantage over classical systems, that's not true. Now, HHL can be used for linear programming and regression, kernel methods, support vector machines, recommendation systems, to calculate the expectation value of Hermitian operators, linear differential equations, deep neural network hyperparameter tuning, quantum machine learning, and also machine learning for quantum systems. Now, quantum machine learning and machine learning for quantum systems are two different things. In machine learning for quantum systems, you are using machine learning to design and better quantum systems. Now, what people don't tell you is also that quantum state preparation has an exponential disadvantage. Quantum measurements also have exponential disadvantage. Quantum machine learning is best used as a subroutine in other quantum algorithms. Now, linear algebra like matrix multiplication and matrix inversion are at the core of machine learning. This is what quantum machine learning is entirely all about. Now, classical matrix inversion and matrix multiplication don't take order n cube. People assume it takes order n cube, but it is worse. It takes order n to the power 5 into square of log n. Now we have achieved linear or log linear complexity with our modified HHL algorithm with full decoding of results. We have achieved true exponential advantage with the modified HHL algorithm, which I am going to show you right now. Now, this is running on a test system, and this is 1,000 times slower than our production system, and it is also 100 times less accurate. Now, and 100 times less costly also. We created this test environment at a very low cost just so that we could show you large scale problems that we can solve with our quantum systems. We are using quantum phenomena and not some classical algorithms like sampling or Monte Carlo, Markov chain Monte Carlo, or simulated annealing or whatever. We are using pure quantum phenomenon. Now, the thing to note is that for us, mid-range problems are around 1 lakh variables qubits or 1 million qubit of variables. For us, large-scale problems are with 100 million variables, 1 billion variables, and in some cases 1 trillion variables. Now, that is what I want you to note, but today I am going to be showing you two examples with 1 million variable matrices. Matrices of the size 1 million by 1 million. Okay. The first thing is matrix multiplication, which is a byproduct of our modified HHL algorithm. and let's run this. Now remember, I told you this is linear or log linear in execution complexity, and it is true exponential advantage in quantum machine learning. That's it. It took 2,765 milliseconds on a test environment, which is 1,000 times slower. Otherwise, it would have taken something like 2 milliseconds or 3 or 4 milliseconds in the production environment. Now I'm going to do a matrix inversion of a matrix of 1 million by 1 million size, and then I'm going to print the first 10 rows and columns to show you that the identity has been achieved in the first 10 rows and columns. Now this will take some time, so I'll pause the video in between. Please be patient. Yep, there it is starting. It is polling and sampling at intervals of 3 or 4 seconds. So I'll let this continue. There it has solved the problem in 65 sampling by taking 65 samples in 160 seconds, and we have verified that the first 10 rows and columns of the result matrix in matrix into the inverse is actually identity. So all our systems are hosted in our data centers and custom built to order. This is all we had to show you today. This is the true exponential advantage with quantum machine learning and HHL algorithm, using a modified HHL algorithm implemented over quantum phenomena based systems. Now that's all we had for the demo today. If you have any questions, you can email us at info@automatski.com. Thank you.